On paper, a simple bottle of phenol, a common antiseptic, and you want to transform it into something more complex, like the fragrant precursor to aspirin, salicylaldehyde. On paper, adding a single carbon and an oxygen atom to a ring seems straightforward, but nature doesn't like making things easy. How do you force a carbon atom to latch on to a stable benzene ring exactly where you want it?
In 1876, Carl Reimer and Ferdinand Tiemann discovered a clever trick using nothing more than chloroform and a strong base. This is the Reimer-Tiemann reaction, and the secret to its success lies in a high-stakes chemical middleman that shouldn't even exist. Let's look at our starting materials. We have phenol, our hexagonal ring with an OH group, and we're dropping it into a solution of potassium hydroxide and chloroform. Notice what happens first. The hydroxide base isn't interested in the ring yet. It goes straight for the chloroform molecule. It plucks off a hydrogen atom, leaving us with a negatively charged carbon. But this intermediate is unstable. Almost immediately, it ejects a chloride ion to relieve the tension.
Watch what's left behind, a neutral molecule called dichlorocarbene. This is our middleman. It has only 6 electrons in its outer shell, making it desperately electron-hungry. In the world of organic chemistry, this makes it a potent electrophile, looking for any excuse to grab on to a pair of electrons. Meanwhile, let's look at the phenol. In this basic environment, the hydroxide has stripped the hydrogen off the phenol's oxygen, turning it into a phenoxide ion. This is crucial because it pumps extra electron density into the ring, specifically at the ortho position, the spot right next to the oxygen. Now, the dance begins. The electron-rich ring attacks the electron-poor carbene. As you see them bond, the aromaticity of the ring is temporarily broken, a high-energy, unstable state. But the ring is resilient. It quickly kicks off a hydrogen atom to regain its stable, aromatic circle, and we're left with a dichloromethyl group hanging off the side. But we aren't done. We want an aldehyde, not a pair of chlorines. This is where the water and base in our flask come back into play. Through a process called hydrolysis, the 2 chlorine atoms are swapped out for oxygen. Picture the chlorines leaving and being replaced by a carbonyl group, a carbon double bonded to an oxygen. Finally, we add a little acid to the mix to put the hydrogen back onto our phenoxide, and there it is, salicylaldehyde. The beauty of the Reimer-Tiemann reaction isn't just that it works, it's the elegance of the middleman. By using a base to create a highly reactive carbene, we turn a stable solvent like chloroform into a precision tool for building complex molecules. It reminds us that in chemistry, the most powerful transformations often happen through the species that are the most fleeting. Next time you see a bottle of aspirin, remember that its chemical lineage likely started with this clever, electron-hungry dance.